So welcome back. The second speaker this morning is Ronggang Shi from Shanghai Center of Mathematical Science of Fudan University. So he will talk about one-parameter diagonal group action on homogeneous spaces. Okay. Welcome.
Thanks for the introduction, and thanks for the organizer's invitation. It's a very nice place. It's a continuation talk from Anish Ghosh's talk yesterday. As not everybody here works on homogeneous dynamics, so I will give a gently survey talk. During the talk, if you have any questions or comments, please feel free to stop me. Actually, I benefit a lot from the questions and the comments of the audience. First, let me introduce the question I'm going to talk about. So let me set up the notation. So G will be a connected Lie group. Which will be fixed. And gamma is the lattice. That means the quotient of G mod gamma has a finite invariant measure. Well, if you are not familiar with the whole theory, just think of the examples given by Anish yesterday. We are going to consider the dynamics of subgroup actions of G on the homogeneous space G mod gamma by left translations. As my title, I'm going to consider the one-parameter diagonal group. So we fix such a group. Actually, I fix a semi-group. So it's AT, T bigger than 0. It's one-parameter, but to be precise, I should say diagonalizable. Well, here, AT means from T to the group F is a homomorphism. So diagonalizable means if we consider the adjoint representation from the group G to the linear group on the Lie algebra, then somehow we assume that the image is diagonalizable. The real numbers. That means there is basis such that the image is the image of F is diagonal. So the dynamics we're going to consider is the subgroup of the semi-group F acting on G mod gamma. Well, the starting point is a very, very general question. It can be asked for any dynamical system. So basically, the question is, given a point in the homogeneous space, what can we say about the trajectory? So the trajectory is denoted by fx. It's just the other point, atx. Well, there are different ways of studying this question. I will not talk about the other directions, but I will concentrate on what I'm interested in. So let me make the question more precise. So I will call it the question 1.2. the question we are going to discuss in today and tomorrow is about one, the trajectory fx equidistributes. For this, I mean, with respect to a homogeneous measure. A homogeneous measure. When I talk about the equidistribution, I mean with respect to a homogeneous measure. So let me give the definition of a homogeneous measure. So here's the definition. So a probability measure nu on G mod gamma, we say it is homogeneous. If the following holds. Homogeneous basically means it's similar to G mod gamma, but maybe not the whole thing. So if there exists a subgroup S of G, and S is closed, and a point in the space such that nu is supported on the orbit of this group, and nu is S-invariant. Under these two assumptions, actually the orbit is closed. Sorry. Thanks for the question. It's equals 1. That's the definition of a homogeneous measure. Now let me explain what do I mean by equidistributes. So, sorry. Maybe it's better to. I mean, X is okay, but let me say why, just to make a difference. So let me give the definition of what do I mean by fx equidistributes. With respect to nu. Nu is a probability measure. That means I will give you two ways of saying this. The first one is we consider the trajectory of the points, and we put the direct measure at ATX. Then we add them up. That means this goes to nu in the weak star topology. So let me give more words to this. That means for any compactly supported function on G mod gamma, if we consider the time integral, that means the integral along the orbits, then as t tends to t, it should be divergent to the space integral of with respect to nu. That's the question we are going to talk about. Well, it is in general a very difficult question. So let me give some examples. It's one of the simplest examples that I have. Consider G mod gamma is equal to SL2R modulo SL2Z. And consider of F is given by AT equals e to the t, e to the minus t. And consider the following two examples. First one is x equals, say, this one. 1 cubic root of 2 or x equals 1 pi 0, 1. The difference is that first one, this is algebraic. In the second one, this is transcendental. So I think the question whether the orbit equidistributes with respect to, here the only possibility is the probability higher measure. That means the G invariant probability measure on G mod gamma I think it's unknown, but I think it means here I'm intentionally put a cubic root. For the square root, no, it's not true because this number is badly approximable. This phenomena said that a typical trajectory is very difficult to predict. So now it's the real question we are going to talk about. So it's the question 1.3. So given a probability measure, given a probability measure nu on G mod, you can say Ronggang measure. Sorry, I use the same notation nu here. What? You mean for generic number? Yes, if it's for generic number, then we know that it equidistributes. It just follows from the work of Ergodic theorem. Because somehow it's the unstable Hart spherical subgroup of my semigroup. So I will make the comments more general, in a general context. So given a probability measure nu, or even Ronggang measure on the homogeneous space. So we want to answer the following question. When does the trajectory equidistributes for new generic x? New generic means almost every point. In the example, the dynamical system is Ergodic actually mixing. So we use the Ergodic theorem to give some answers. I just commented. So in the non-trivial cases, in the homogeneous dynamics, according to my knowledge, there are two types of methods to study this question. So let me, because I'm not going to give proofs, at least I'm not going to give proofs today, but let me just mention briefly what are the two methods to study this question. So should be, where is it? Okay, let me talk about the methods. The first one is using random walks. random walks has been extensively studied in homogeneous space, and the breakthrough is made by Yves Benoit and Jean-Francis Lacan. But here, the random walks, what I mean is for solvable groups, for solvable groups. And the people who use this method is David Simmons and Barker Weiss. Well, this method allows them to prove this type of results for fractal measures. Fractal measures generated by the random walk. Say the 1/3 counter set in that sense, in that case. That's not what I'm going to talk about today. What I'm going to talk about is the second type of methods. That's, I will call it the quantitative results. Quantitatively study the push forward of the measure by nu. Because we cannot study points with such measures, but without any quantitative information, I don't know how to prove these kind of things. Well, why quantitative? Because quantitative results allows me to use the Borel-Cantelli. That's why I need quantitative results. But let me give the definition of this push forward, because I'm going to use it many times. I think it's already used in Peter's talk. So again, so we want to define the push forward. We need to look at the value at the test function, say phi, which is continuous and compactly supported. So it's equal to the integral phi evaluated at ATX nu. Maybe let me draw a picture. Say nu is here. It's nu. Then by AT, call it say G. Then we move this part to AT Z. That means the push forward, just the push forward, the point, the measure on the image. That's a picture that you should keep in mind if you don't, if you're not familiar with this notation. Okay, so what can we say? Say it again. No, I mean AT. You see the direct measure. So nu equals delta x. So it becomes if I put another definition, is I put a set, then it's nu AT inverse A. Yes. But here, say nu is the direct measure, then it takes the value here. It's just different ways of defining the push forward. Okay. Now let me give a family of non-trivial results in the setting of the example, which is familiar to homogeneous dynamics people. Let me give an example. In this example, moment gamma equals SL m plus n R modulo SL m plus n z. Here, m and n are positive integers. So the flow we are going to, no, actually no, that's not a moment gamma, sorry. I mean, it's not what I'm going to set up. I'm going to take it like this later, but not right now. Right now, we fix the subgroup, actually a closed subgroup of the, I mean, G is fixed all the time, but we consider subgroup H. H may be a proper subgroup of G, and we consider the one parameter subgroup given by weight. So we also fix the weight. Fix the weight. We call it W. There are two positive, one positive vector and one negative vector. First we give m positive real numbers, then we give n negative real numbers. We assume that their sum are equal. So that if we consider the diagonal matrix e to the s1t, e to the smt, e to the minus r1, this diagonal element belongs to the group H. And then we consider the one parameter group we're going to consider. I will call it FW. Consists of this AT. This one parameter group is used by many homogeneous dynamics people because it's closely related to the finite approximation. So let me give a, now we have dynamics. So next let me describe the measure nu. What kind of measure we want to study? For this purpose, I need to define an auxiliary map, U, from the m by n matrices to my group H, which is embedded in G. So for any matrix theta, it is mapped to a unipotent group. A unipotent element. Here, when M is the rank M identity matrix, then put it here, then put the 1n, here 0, nm. I call it, it is called U theta. Now we fix a point in the homogeneous space. Somehow, the measure nu is just, we're going to consider it in this orbit. Or on this foliation. Well, to make it, it's not difficult to make it a probability measure. We just cut a small piece. Then it's a probability measure in the correct sense. So now we have a dynamical system. in this case is FW, G mod gamma. Now we have a measure. We want to say that for generic points of neo, the trajectory equidistributes. Actually, we can say what's the target measure. So for this, we need to reveal a result of Marina-Ratner. So by a theorem of Ratner, who proves a conjecture of Raghunathan and Dani mentioned yesterday. The orbit closure Hx bar is homogeneous. Homogeneous, an orbit closure is homogeneous means it supports a homogeneous measure and trying to define, okay. Means let me explain what I mean by the orbit closure is homogeneous. That means it equals to the orbit of another group. And there exists actually unique S-invariant probability measure, I will denote it by mu Hx. On Hx bar.
H is the unipotent or H is SLN?
H is, yeah, I should injection, yes. It's a map to that. H is H is this one. G is anything that contains H. Does it answer your question?
You have a homomorphism from SLM plus 1 was some.
Yes, exactly.
And you apply it to H action on G mod gamma.
Yes. I mean,
This one is
actually, H is auxiliary. I mean, I consider this dynamic. What is S? S is just from, okay, now I'm some S. I don't know what S is. There is, if you want to compute it precisely, you need the information of this X. I mean, this X determines the S. Now, here I give the definition of what is called Hx bar is homogeneous. That means there exists a closed subgroup S such that the closure is equal to Sx, and there exists a unique invariant probability measure, S-invariant probability measure on this, supported on this set. Am I ready to state the result? Yes. Okay. Now the theorem. That means we give an answer to this question in this special setting. So for almost every theta, almost every is with respect to the big measure. The trajectory well, here, this is the point. So this is in trajectory, equidistributes with respect to mu Hx bar. Maybe I should give some more examples. Say H equals SL2R. Maybe this is trivial. No, not trivial, but okay, not trivial example. So G mod gamma equals SL3R modulo SR3Z. So H is just here. So this is S3R, how it sits. Let me see. It's not an isolated result. I'm going to mention some related results so that you know something wrong. I mean, it's, okay, W is fixed, X is fixed. Okay, I should say that for any fixed W and fixed X. So we fix the dynamical system, and then for any X, that means in the homogeneous space, we fix the piece. And then we say that almost every point on the submanifold equidistributes. That's basically what it is saying in that theorem. As I said, the proof is through the method 2, quantitative study of the trajectory of measures. So the question is, you may ask, do we know the quantitative results? The answer is yes. I mean, the quantitative result for the trajectory of measures is known. So let me just mention it. To state it precisely, I need to introduce some notation. Because for here, I don't need more notation, but here we need. So because I want to make this nu to be a probability measure, so let me give a density function. Such that f d theta is a probability measure. Is a probability. Here d theta is the big measure. Now okay, let me write down the picture. So it's mn to h, then to g. Then somehow it's mapped to G mod gamma. All the left-hand side is auxiliary. Then here is the dynamics AT. So we put the measure here, f d theta, probability measure. Then it's pushed forward by U. Then it's pushed forward here. I consider H is subgroup of G. So this is inclusion. Now I fix X. I define a map pi X, just the G to Gx. All the way down. Let me give my first remark. Remark, yeah. Remark, okay, theorem, this is 2.1. Remark 2.2. 2.2 is what? I will call it the first one. Is, if we consider all the way push forwards, but maybe I should call it this way. I mean, because somehow this pi x is fixed, and u is fixed. Then it's f theta, d theta. Somehow this is my nu. Explicit what nu is. This converges to mu hx bar. We know this around 20 years ago. I think in this form, I mean, result due to Nimi Shah, who was in Tata Institute, now in Ohio State, and Berkeley. What's the word condition on F? Word. I fix the weight. In that word, it's the weight.
No, the other smaller.
Oh. Okay. F is the probability, that means R1.
That's it.
Yes. Another question that one may ask is, here is somehow measure on DSM. Can we have similar results or the same results for refined measured, say, fractals or curves? Well, but as I said, the measure is by study quantitatively the translate. So the first question is, do we know the quantitative results for the curve measures? The answer is yes. Let me just state what we know. Remark B. M equals 1 or N equals 1. And then we consider curve. To my matrix. Well, we have to add some assumption. So I would say it's non-planar. In this case, it's just a Euclidean space. Non-planar means it's not contained in any proper affine hyperplane. And analytic. Now I have one more thing. Okay, so then we push forward, asymptotic push forwards of, now this time is first the C, then it's U, then it's pi x. This push forward. Here I'm put the big measure on the unit interval. Then at t tends to infinity, this volume measure on the curve equidistributes with respect to the correct homogeneous measure. Okay, this result is due to Nimisha. Well, it's 2 papers actually. So the question that we don't know is the following. Any questions? The question is the theorem, is the point-wise equidistribution holds in the setting of, I would say, the setting of the above remark. Somehow, the question is, okay, whether the point-wise equidistribution true for curves? I want what?
You want to add any M or N?
Okay, even in the simplest case, we don't know. Say G mod gamma equals SL3R modulo SL3Z and H equals Z, and say F equals e to the t, no, at e to the t e to the minus 2t. You know where I put MMN, even in that case. So it's not known. The abstraction well, in the proof is somehow we need some information local. But when we expand the curve very large, it close to a straight line. Well, it shows the result that he looks at the whole curve. The whole curve is still a curve. A small piece is like a straight line. But straight line, as it can be seen from statement, is the obstruction. Another question is, okay. Is the question, is the result of Anish clear?
Yes.
Okay.
Is the question you want to drop the assumption that N or N1 or what do you want?
And yes, I mean, in the setting of remark B, can we prove that almost every point on the curve equidistributes? That's the question. What? Yes. The theorem is about okay, shall prove that the curve, if we put forward, it equidistributes. I want to ask whether for generic points, the trajectory equidistributes. For generic points. With respect to the big measure. Of course. Is that clear?
You replace the big measure with a direct mass for almost every point.
Yes.
Right?
Yes.
Okay.
Yes. That's the general setup. That okay, we given a measure nil on homogeneous space, whether generic point equidistributes. But the way we study this question is to study the measures. So first we want to know whether the result holds for the measures. And then, I mean, somehow, due to the work of Marina Ratner, I mean, the measures are easier to study than the trajectories, than the trajectory of points. Yes, yes. Yes, 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 exactly. Another question is question 2.3, question 2.4. No. Where am I? What is 2.3? Okay. Another question we can ask is it possible to prove? Maybe I noticed that if I state very precisely, like writing a paper, it's difficult to read. So I will say something that is maybe makes more sense. Is it possible to prove pointwise equidistribution effectively? Well, what do I mean by this? Let me give the answer, partial answer, so that you know what I mean. So the partial answer is, I will call it the theorem 2.4. A partial answer to the previous question. So in this case, we assume G equals H equals the special linear group. And gamma is the analysis. As before, we fix W. Now we say, then the conclusion is given any x in G minus gamma, and what? And epsilon bigger than 0, and the test function. Now I need, equidistribution is with respect to compactly the continuous functions. But to get effective result, continuous function is not good. Continuous function can be very bad. Now I put the smooth assumption. That's the assumption. It's actually natural settings. Then the conclusion is for almost every theta in the matrix, we have either the ergodic average as before, and then we evaluate phi at ATX. Oh, sorry. This is AT U theta x. Effectively, well, we know it should converge to the space integral of phi. Effectively means we know the error rate, error term, plus little o. It's very good error term. This is all depends on x, of course. That's maybe the okay. So this result is due to Kallenbach, Dimitri Kallenbach, myself, and Berg-Weiss. For the lattice gamma equals SLM plus NZ, and the general gamma is proved by myself recently. Does the result make sense? As I said, it's an example. So our aim is to generalize this, or maybe, but I will see. It depends on the time, whether I'm going to generalize this or give the proof. The experts, it's not difficult for the experts to imagine something more, because I put a square root of t. So experts in probability theory ask, do we have central limit theorem? The answer is yes. And what else can we say? I need to erase it first so that it can be tried. Now let me state the central limit theorem. I think it's probably make more sense because our summer school called the probability theory. So it's central limit theorem. So theorem 2.5. The setting is exactly the same. Not quite. Shall I state the central limit theorem? Okay, but let me try to do that. Again, central limit theorem is not about the typical trajectory. Central limit theorem is about a probability measure. It's about a random variable. So let me fix. So the notation and the assumption as above. Yeah, above makes more sense, I feel. Now we need to fix now we need to choose a convenient probability measure. Now F is a map here. I assume that F is smooth and compactly supported. The F d theta is a probability measure. Okay. Okay, central limit theorem is about random variables. So what's the random variable? So then the conclusion is, I mean, for experts, it's not difficult to write it down, but let me write it down. So then the random variables, random 1 over square root of t. Where is it? Okay, it's phi at u theta x dt. I should say what's the law? What's the law is? With law, I would say it's mn and f d theta. This is my measure. Okay, a random variable is from a probability space to real lines. That's a map. I say random variable because there is a parameterized by t. That's the parameterized. So this is a sequence of random variables. Converges in distribution to normal distributions. Okay, so I need to assume one thing, otherwise it doesn't make sense. Maybe, okay. Now let me see. Okay, do I need to? Yes, I need to assume something. And assume that mu G mu gamma phi equals 0. And so assume that actually, I don't need but this is very restrictive. Maybe I should say phi belongs to CC infinity plus a real number. I mean, the constant is not an abstraction for the result. Otherwise, the integral 0 is, I mean, it doesn't have to be smooth and compactly supported. We can just put the function phi, then subtract the mean. Two moments. Okay, so it has expansion moments, if you want to say. I mean, it's bounded function. In distribution to non-distributions with mean 0 and variance sigma. I didn't write it down because I don't remember how to write it down. But it's just normal distribution variance sigma. Var sigma equals 2, 0 to L. Oh, no. Equals 2, 0 to infinity phi at u theta, no, atx. Somehow the variance does not depend on the choice of my measure, so it can be checked that this is bigger than 0. Hold on, sorry. Am I writing it correctly? Okay, thanks. That's what I think you're right, but I don't have square. It's this. Okay, it can prove that this is bigger than 0. Wow. Somehow in the central limit theorem, should characterize whether the variance is 0 or not. If it's 0, then it's degenerate. That's interesting. So moreover, okay, so, yeah, I think you're right. That should put another, hold on. 0 to infinity should be dt, then there's another x. Okay, let me just write it again. Now, first we take an integral of x. That makes sense, right? Then we put another integral about 0 to infinity dt. That makes sense. Thanks. Moreover, well, we don't have if and only if. Somehow our dynamical system is partially hyperbolic. In the Anosov case, they have if and only if characterization of the zero variance. But we only have sufficient condition. So, okay. Sure. So, okay, you mean you want this part bigger, right? Okay, sure. No problem. So let me write so this is from 0 to infinity, actually twice. This should be put twice. Then from 0, no, from then is x. It's phi atx, phi x, then d mu x, dt. It depends on your notation. I mean, yeah, it means somebody put sigma square, but I prefer, it's bigger than 0. Yeah, somebody sigma squared, but because somehow, I'll say, I never took a course in probability theory, so I just learned it by need, so I just. Does it make sense? Now we give characterization of the sigma. A sufficient condition. If sigma equals 0, then I will give a name, and then I explain what I mean. Then phi is, I will call it dynamically null. With respect to the dynamical system, G mod gamma. That means for any F invariant probability measure mu tilde, we have the integral of this, I will call it is equal to 0. That means if there is an invariant measure, an invariant probability measure, such that the integral is non-zero, then sigma is positive. That means the central limit theorem is non-degenerate. Not any, I fix the weight W, and this is my FW. The group U is not pay a role. It's not pay a role in the variance. It's pay a role in the central limit theorem. The central limit theorem, there should be law. Law is given by the U. Okay, so let me say this. So, okay, let me give a remark for the contributors. You mean how do I prove the, how do I?
No, because point is that usually what happens in hyperbolic dynamic systems is that when you prove the central limit theorem,
yes,
the alternative is that either the variance is positive, either sigma is positive, or your function is a coboundary.
Yes, exactly, yes.
No, but it's not what you wrote. You wrote that.
I didn't write it down because there is an intermediate theorem I didn't state. Yes, that's a.
There's the Shi theorem. That is this conclusion is equivalent to the function being a coboundary or not?
No, it's not equivalent. Okay, let me say this. Okay. I think you're right. Okay, I didn't state it here.
I cannot be right, I just asked a question.
Yes, I know. Yes, I'm answering your question.
Okay, yes.
So a statement I didn't say here is that sigma is equal to 0 if and only if phi is a coboundary in L2. Okay. Okay, I will make it as first remark. Sigma equals 0 if and only if phi is a coboundary in L2, gamma gamma mu. I know. No, okay, it's a theorem. I mean, in this, the setting is the same. The theorem is phi is L2 coboundary. Implies phi equals phi tilde, or some phi tilde belongs to CC. C infinity gamma gamma. I just didn't state it here. Okay, sorry. I was saying, if and only if phi is a coboundary, that's what I'm saying. That's what that's a very good point. I want to omit this part, but thanks for asking. The second remark is about the contributors. Okay, the central limit theorem is okay for gamma equals this one. The central limit theorem, well, without characterization of sigma, it's due to, hold on, let me write down. Where is it? Because it's Vershik and Kaimanovich. In that case. And then the central limit theorem, the general case. I would say other. I think they prove it for the equal weighted case, right? I mean, equal weighted case, yeah, I think you're right. Sorry, I mean, if equal weights make sense, I mean, equal. Since the copia is not here, so I just sorry, I don't know how to spell them, so I should give somebody. There's another nice result. Do I have time? Yeah, I still have 5 minutes. Okay. Now I will state the multiple Ergodic theorem. That's my favorite theorem, actually. Okay. First, let me write down theorem. Write down name, because if maybe you don't know what I'm saying. But now I'm going to state. Okay, it's 2.6 is about multiple, not multiplicative. It's multiple pointwise Ergodic theorem. Count effectively. It's somehow a generalization of this one. This one is Burkhoff. There is multiple. Well, I'm erasing the blackboard. Let me state the history of multiple Ergodic theorem. Multiple occurrence is proved by Hillel Fussenberg. Then in his famous book, he asked the question of multiple pointwise Ergodic theorem. Actually, he asked the double pointwise Ergodic theorem. Then theorem is proved by Bergan in 1989. That's a big breakthrough. Now, the general multiple Ergodic theorem is known in some special cases. Say for homograph system. Homograph, say Bordering shift. It's proved to be true. I mean, for general multiple Ergodic theorem. And distal system is proved by some Chinese mathematicians, Wen Huang, Shong Sao, Xiang Dongye, and some other people. Now, what I'm going to state is, okay, no. So multiple is on the pointwise. So how about the mean? The mean Ergodic theorem is actually very, very, very better understood. So for commuting maps, it's proved by Tau. And for non-commuting, say unipotent group action is by, what's his name? I forgot the name, so but it was known. Now I'm going to state the pointwise Ergodic theorem. So let me, it's not that, okay. Multiple means for multiple average, multiple function. So let me fix by one. I will state K multiple. So their functions belong to CC infinity, G mod gamma plus R. Their functions, and then I should have a base point. Okay, so and x1, xk, sorry. Multiple, the statement is kind of needs a lot of information, but they are really what we need. Belong to G mod gamma, also what? So maps. What are my maps? Oh, sorry, I should write the ladder, so I will write ladder here. So the maps is T1 equals, how to say it? Somehow, I should write to the exponential way. So let W has this form. Wi equals Si1, Sim, and Sri1 is minus, it should be R1, Rn. This is my Wi. I consider it as the algebra of G. So it's the algebra of M plus N. Diagonally. So Ti equals exponential of W1 till Wi plus. Sorry, should be plus. The setting is kind of ugly, but basically we have k functions, k maps, k functions, k maps. Now, another assumption is done. So the conclusion, theorem, it's by myself and René Ruch. René Ruch is postdoc in Technion, and he was also a student of Manfred Einsiedler. For any subsequence, now what Nm of integers and epsilon bigger than 0, we have the following. It's just the pointwise Ergodic theorem. Okay, so basically, what I'm stating is a multiple version of this one. A multiple version. Multiple version is like ugly. Maybe a little bit ugly, but sorry. Just tolerate me for a couple of minutes. It's T1, N1, U theta, X1. So it's phi k, Nk. Phi k is Pk, Nk, U theta, Xk, dt. That's the multiple Ergodic average. Now it should be equal to the product of space integral Sorry. Okay, I think I made something wrong. I should say sum. If I do sum, it should be. Okay, sum I from 1 to n, the 1 over n, in this case, now no dt, plus little o, the same. For mu, no, so for almost every theta. Okay, now I finish and I stop here. Thank you.
Comments?